So today we're going to be talking about inverse functions. So we're going to learn about what is an inverse function, how do you know it's an inverse function. We're going to start with the explorers, and then I believe we're going to go through about explain one. Today we're going to be talking about modeling as our mathematical practice, and really this is where we represent our data and we use math that we know to solve everyday problems. In this particular one, we're going to see a lot of diagrams that we're going to use to model our mathematics. All right, so the first explore, understanding inverses of functions. So recall that a relation is any pairing of the elements of one set, the domain, with the elements in a second set, the range. So let's underline that. Pairing of elements, one set the domain, second set the range. Remember, the domain is your x values and the range is your y values. That's something you probably learned in Algebra 1. The elements of the domain are called the inputs. So domain is also inputs. The elements of the range are called the outputs. A function is a special type of relation that pairs every input with exactly one output. So I might even underline that twice. A function pairs every input with exactly one output. If a function is in a one-to-one function, no output is ever used more than once. So one-to-one, no output used more than once. In a many-to-one function, at least one output is used more than once. I know we underlined a whole lot there. There's a lot of review definitions there. An inverse relation reverses the pairings of a relation. Okay. If a relation pairs an input x with an output y, then the inverse pairs the input y with an output x. So basically what we end up doing is we end up switching x and y. That's not a bad thing to write kind of out on the left side, making an annotation in your notes. The inverse of a function may or may not be another function. If the inverse of a function f of x is also a function, it's called an inverse function. It's written f inverse of x. If the inverse of a function is not a function, then it is simply an inverse relation. All right, so here's some modeling of mathematics. We're going to use what we call mapping diagrams. To show a function and its inverse, complete the diagram for the inverse of the function. Is this function one-to-one or many-to-one? Explain why. So may remember our big key here is we have to switch the x and the y value, or switch the domain and the range values. So you'll notice that if the 4 was the domain, the range was the -2, they flip-flopped them. So if our domain is 0 and our range is -3, and the inverse, our domain is -3 and our range is 0. And then if a domain is 1, range is 2, our domain flip-flops, domain is 2, range is 1, and then double check the 4, 1 became 1, 4. So is the function one-to-one or many-to-one? Explain. So we know that there's only one place that the actual function maps to a single value. So we know that this is a one-to-one function. So we would say the function is 1-to-1 because no output is used more than once. Used more than once. Is the inverse function also a function? Again, very similar. It's each one is mapped to each x value is mapped to a single y value, so we know that their outputs are only used one time. So inverse is a function because for each input, only one output. All right, so a little bit different in this one. We're going to try to map again. So -4 to 2 is -2 to 4. 0 to -3 is -3 to 0. Ooh, 1 goes to 2. So that would mean 2 would have to go to 1, but 4 also goes to 2, so 2 goes to 4. something different happened in this one. So they're asking if it's 1-to-1 or many-to-1 in the function. We would say many-to-1 because this maps to, there's two x values that map to the same y value. This is okay. You can have two x's map to the same y. So we would say function is many-to-1 because two domains or two inputs have the same output. But the reverse is not true. If a domain maps to a single domain maps to two different range values, then we know that it fails being a function. So the inverse is actually not a function. It's the inverse of a function, but the inverse is not a function itself. So inverse, not a function, because one input maps to two outputs, two different outputs. So it says the graph of the original function in step A is shown. So they plotted those points from the step A. Note that the graph also shows the dashed line y equals x. Write the inverse of the function as a set or order of pairs and graph them. All right, so here's my function. Remember, our big key again is to switch x and y. So I'm going to swap the order of these. So -2, -4, -3, 0, 2, 1, 1, 4. So instead of mapping, we wrote it in kind of a set notation. I'm going to go ahead and graph plot these points. So out -2 and down 4. Out -3 and up 0. Out 2 and up 1. And out 1 and up 4. And you'll notice that on that dashed line right there, if I were to fold it, they would be symmetric. They would fold right on top of each other. So that's what it's asking us, what do you observe about the graphs of the function? It's inverse in the relationship to the line y equals x. It's basically a reflection, or it's an axis of, it's a line of symmetry. And it makes sense because the x values and the y values ended up switching places. So we just need to write all that down. So the graphs are reflections across y equals x, which makes sense because the x and y coordinates are switched. Are switched. All right, so this is what we talked about yesterday. We've got the composition of two functions, f of x and g of x, written f of g of x and read as f of g of x, is a new function that uses the output of g of x as the input of f of x. Remember, we start from the inside and we work our way out. For example, consider the functions f and g with the following rules. Now, this is a little bit different context than what we put it in yesterday. So add 1 to the input and double the output. So we'll notice that g of 1, we have to double the double the input. So if we're putting 1 into g, we double it, so we get a 2. So then we take that 2 and we substitute it in for g of 1 into the f, and f said we had to add 1, so we got a 3. So you can also find g of f of x. Notice that when we put in a 1 into f, which said we had to add 1, we get 2. Then we can take that 2 and substitute it in for f of 1. And g was to double the input, so we're going to multiply that by 2, we get 4. So for these two functions, you can see that f of g of 1 is not equal to g of f of 1. You can compose a function in its inverse. For instance, the mapping diagram illustrates f inverse composed with f of x, where f is the original function from step A and f inverse is its inverse. Notice the range of f of x serves as the domain of f inverse of x. Complete the diagram. What do you notice about the outputs of f inverse composed with f of x? Explain why this makes sense. All right. So basically, these values here are the range of f and the domain of f inverse. So remember, if this is the domain, I need to get this in here as the range because we're switching our x and y values. So it should be -4, 0, 1, and 4. So what do you notice about the outputs of this? So basically, the outputs compared to the inputs, you'll notice that they are actually end up being the same. So they actually end up equaling. If this was x, this would also be x. So again, that line that we saw back here, it's symmetric or has a reflection about that line, y equals x. It's all kind of connected there. So let's see if we can summarize that exactly. So the outputs of f inverse composed with f of x match the inputs and why it makes sense. So the inverse basically takes that output as an input and assigns it back to the original function's input. So the composition takes an input, assigns it to an output, and then assigns it back to the original input. So makes sense because the inverse takes the output as an input and assigns it back to the original function's input. Okay. So let's go ahead and reflect on what we've done so far. So what is the relationship between the domain and range of a relation and its inverse? So basically, we know that these two things are swapped in an inverse, right? So the range of the original is the domain of the inverse. Sorry. And the domain of original is range of the inverse. In step D, you saw for the inverse functions f inverse of f of x equals x. What would you expect for f of f inverse to equal? Explain. So it really, in theory, should equal the same thing because of the symmetry there. So f of f inverse of x equals x because f inverse of x maps the output back to its input. Sorry. Its input. So f of f inverse of x will map input back to the input back to the input of f inverse of f inverse. So f of f inverse of x equals x because f inverse maps output back to its input. So f of f inverse will map the input back to the input of f inverse of x. All right, now we're going to explain. We're only going to do one explain today, and we're going to skip the other explain. So we're going to find the inverse of the linear function. I do this a little bit differently than they do. I switch some of their steps. And I'll show you kind of both ways, the way that the book does it and the way that I do it. So every linear function, f of x equals mx plus b, remember this is just your y equals mx plus b, where m does not equal 0, is a one-to-one function. So lines are one-to-one. So its inverse is also a function. To find the inverse function, use the fact that inverse functions undo each other's pairings. So these are kind of the steps. If you forget what you're doing, this is what you would come back to. First, you're going to substitute y for f of x. I agree with that step. Then it says solve for x in terms of y, and then switch the x and the y. I would reverse these two steps. I'd probably switch my x and y and then solve for y. And then go back and replace y with f inverse. And then it says we should verify that our functions are inverses by composing them and making sure they equal x. All right, so let's step through this kind of the way they did it, and then I'll kind of show you my method too. It says they're going to start by replacing f of x with y, which is what they did here. Then they went ahead and solved for x. So to do that, they started by subtracting that 4, which is what they got here, and then they divided by 3, which is what they got there. Then they interchanged x and y, so they flipped their x and their y, and then they replaced with f inverse. Here's what I would have done different. In this step right here, I would have switched it to x equals 3y plus 4. Now I'm going to solve for y. So x minus 4 equals 3y. Divide by 3. And then switch that to f inverse, and then I tend to bring it over to the left side. So theirs was 1, 2, 3, 4 steps. Mine was 1, 2, 3, 4. So it's the same amount of steps. It's up to you. I like thinking when I have to do an inverse, I immediately switch the x and the y. So you'll probably see me do it this way. Then they want us to verify. So we're supposed to show that the compositions end up equaling x. So here's what they did. They did f inverse with f of x. So they took f of x and replaced it with 3x plus 4. Then they wrote out f inverse, which is what we found here. So instead of writing x, they wrote 3x plus 4 minus 4 over 3. So that we know that those 4's cancel. Then in this case, the 3's cancel were equal to x, so it verified. All right, now we're going to compose the other direction because they're not actually inverses unless they compose both directions and equal x. So I'm going to substitute f inverse in. So that's the x minus 4 over 3. Then I'm going to write out the f function. So it's 3 times the x, which we replaced with this, plus 4. Then I'm going to see what I can do to cancel. So my 3's cancel. That's what they have here. Then the 4's cancel, and then it in fact equals x. All right, we're going to try this kind of with a little bit of a skeleton, okay? And I'm going to do it both ways, their way and my way. So it says replace f of x with y. So they said y equals, and we're going to go ahead and put in the 2x minus 2. And then we're supposed to solve for x. So to start solving for x, I would add 2 over. And then we're going to divide by that 2. So and then we're supposed to interchange the x and the y. So we would interchange, so they make it y equals x plus 2 over 2. I would have gone and done this. So I would have said x equals 2y minus 2. I switched my x and y right off the bat. Add my 2. Oops, sorry. Now divide by 2. And then now we're in the same place. We switch it to the inverse. So up to you which way you do it. They want us to go ahead and verify. So we're going to start by putting f of x in first, which was the 2x minus 2. Then we're going to put in the inverse function here. So the x is already in there for us. So we do a plus 2 divided by 2. We know that these 2's cancel, and I'm left with 2x over 2. These 2's cancel, I'm left with x. So it worked going that way. Now we've got to put in the f inverse. So we get x plus 2 over 2. Now I'm going to put the f function around this. So it'd be 2 times this x minus 2. These 2's cancel. I'm left with x plus 2. Those 2's cancel. I'm left with x. So it did, in fact, work, which means we actually did the problem correctly. Oh, it looks like what was the instructions? We're supposed to also graph the function and its inverse, which we didn't do on the first one. So let's actually do that, okay? So this one right here is a line, so we know the y-intercept is -2. We're going to count up 2 over 1, up 2. I do it a couple of times because it's really hard to draw lines on this digitally. Oops. Oh, I did that right. Okay. So there is, oops, mine's curvy. Hopefully yours isn't that curvy. All right, let me do the other line. So this other line's a little bit trickier. I would probably rewrite this as 1/2 x plus 2 over 2, which is really 1. So my y-intercept is 1, and I'm going to go up 1 over 2, up 1 over 2. That would be my second line, or my inverse line. All right, let's reflect on this, what we've done a little bit here. So, what is the significance of the point where the graph of the linear function and its inverse intersect? So what they're talking about is right there and right there. What's the only place where the two functions, the function and its inverse, actually have the same value? So, and they always will intersect on the line y equals x. So they intersect on y equals x, which is where the value of the function, oops, sorry, it is acting silly. Uh-oh. Go back here. Okay. The value of the function and its inverse are the same. All right, the graph of a constant function f of x equals c for any constant c is a horizontal line through the point 0 equals c. Does a constant function have an inverse? Does it have an inverse function? All right, so first of all, let's draw a picture of that. Let's pick a random c value. So we're going to pick a random positive c value here. So this is the function f of x equals c. Well, I would pick another positive value, or pick the same positive value, but for the x's here. But you'll notice that right here, I have more than one y value that's true for those x values. So therefore, my inverse is not actually a function. It does have an inverse, but its inverse is not a function. Another thing that they didn't really show us in this lesson is the vertical line test. It's a quick way to show us whether or not something's a function. If I can run a vertical line through something, and it only touches once, meaning it has one y value, it's a function. But you notice if I tip this on its side, that's no longer a function, it fails. If I were thinking about the vertical line test with this line here, it would fail because my vertical line touches the function more than one time. All right, so we're going to kind of write that out and summarize that. So does the constant function have an inverse? Yes. Constant function has an inverse. The inverse is not a function because its input has more than one output. All right, I think we have one more to try together here, and then we're going to be done for the day, okay? So to find the inverse, use composition to verify that they're inverses, and then graph the inverse. So I'm going to go ahead and graph this to begin with, get that out of the way. So I know I'm up 3, and I got to count down 2 over 2. So there's my original function. All right, first thing I'm going to do is put in y for f of x. I'm really cheating there. I'm going to go ahead and switch x and y because that's the way I like to do it. I'm going to go ahead and subtract the 3. And then we're going to divide by the -2. And we're going to rewrite it in inverse notation. I could even go as far as writing it like this. Oops, sorry. Over -2, double negative is going to go positive because I'm going to now have to graph that. Okay, so I'm going to graph it in a different color. I'm going to work fast because the baby's starting to fuss here. So we've got to go 1.5. And then we're going to go down 1 over 2. Oops, should have done that more than one time. All right, then we're supposed to verify with the composition. So I'm going to start with f of f. It doesn't matter which one you do first. So this says I'm plugging f inverse in. So my f inverse was x minus 3 over -2. Then I put my f function in. So -2, x minus 3 over -2 plus 3. Those cancel. I get x minus 3 plus 3. All right, and then we go the other way. Sorry for the crying. I promise I'll pick them up in just a second. F inverse, and then we've got -2x plus 3 gets subbed in. My F inverse was the x, which was the -2x plus 3, minus 3 over -2. These cancel. I'm left with -2x over -2. Those cancel, and we've got x. All right, so what you guys need to do to finish up for today, it's weird that my writing is still there, is you need to do, elaborate 7, 8, 9. You get to skip 10, and then 11. Okay, and then that'll finish up the lesson for today.